Salma madam. Salma madam.
Hello. Good morning, sir.
Madam, I request you to introduce our speaker, Ishwarmurthy garu.
Yes, sir.
Proceeded.
Shall I start, sir?
Proceed.
A very good morning to everyone. I am Salma Sultana, Assistant Professor EC Department, Gudlavaleru Engineering College. A warm welcome to second session of today's program. It's my immense pleasure to introduce today's guest speaker, Dr. K.V. Ishwarmurthy Garu. Dr. K.V. Ishwarmurthy graduated with Bachelor of Engineering in 2005 from Bannari Amman Institute of Technology. Graduated with Master of Technology in Sensor System Technology in 2009 from Velluru Institute of Technology. And he did his PhD in Instrumentation and Applied Physics from Indian Institute of Science, Bangalore in 2016. He was also a recipient of prestigious fellowship, including contingency funds from the Ministry of Human Resource and Development, Government of India. He is currently working as faculty of Electronics Engineering at IIIT DM Kurnool and Kanchipuram campus. Dr. K.V. Ishwarmurthy has extensive professional experience in teaching, research, and industry. He has published his work in reputed journals like Journal of Electrochemical Society, Skin Research and Technology, ECS Electrochemistry Letters, ECS Journal of Solid State Science and Technology. He also presented his work at International Conference, ECS Meeting, Chicago, USA, for which he received travel grant from Indian Institute of Science. He presented in national conferences like ICON 2017 SRM University, Chennai, and ICPSCI 2017 Savita Engineering College, Chennai. Dr. Murthy worked as Senior Research Fellow at Indian Institute of Science and Design Engineer at Ensemble Tech Private Limited, Chennai. Dr. Murthy has memberships in various professional societies like IEEE, ECS, ISOI. On behalf of EC Department, Gudlavaleru Engineering College, I welcome Dr. Murthy Garu to present his talk titled Powering IoT Devices. Thank you.
Thank you, ma'am, for the introduction. And I'll thank you, Dr. Kamraj Garu, for giving the wonderful opportunity to deliver this lecture. Sir, now you are able to see my screen?
Yes, sir.
Yes. Today lecture is about powering IoT devices, and after this we are going to see some packaging. Then after this, some of the protocols. Now Lakshmi ma'am took up the communication protocols, but there are some other protocols like I2C, SPI, UART kind of thing, which can be communicated between the devices, right? So why it is required? Why need to require the powering of devices is necessary to know about that? Because the IoT device of a lifetime of IoT device depends upon the power source. Let's say if you are have a battery for IoT device, then this lifetime of IoT device until the battery lasts, that is a lifetime. And it is not connecting some sensors and actuators with some microcontroller and microcontroller with gateway and gateway to some cloud, right? So we should know how the practical IoT devices should be, and what are the major consideration, because power is a major consideration in the IoT device, and major research is going on how to optimize the power and power up and power less power architecture. What are the things are the different things going on? Only this how to the power the devices, IoT device. So here for any device, how we can evaluate this IoT device? We can evaluate basically by using physical electrical functional elements like physical size. Let's say what is that miniature assemblies having battery compartment or socket, or how to it can able to harness the power and how we can able to get this power source. And again, operating temperature, because whether the IoT device going to operate in various wide range of temperature from indoor to outdoor, or body worn or implantable, or to extreme environments, right? And functionality. What is the functionality? It is going to sense, or is going to collect the data, or is going to do the radio communication. And what are the components in that? Sensors, radios, microcontrollers, microprocessor, including human interface some cases, right? And what is the purpose? So remote monitoring or diagnostic, preventive maintenance, controls, gathering the statistics, and machine to machine learning. So it have these are the things for considering the powering the IoT source regarding physical size, operating environment, functionality, components, and purpose. So this is the important thing. We need to select the powering. Let's say, because this is the first, I'm going to make the disclaimer. So most of the things taken by some of the books and some of the papers, because my area is biosensors. I'm not working on this area. So first disclaimer is none of these presentations available here is not developed by me, but some of the contents I added from books. So this is the first disclaimer. So what are the power sources for IoT? So we know this storage. We have the batteries, micro fuel cells, micro heat engines, super capacitors, and distributions. We can say from wires. There's wires from the power lines and electromagnetic RF. And harvesting, we can able to harvest the power from solar, wind, hydro, mechanical, and thermal. So these are the power sources available for the IoT. Let's say you know the batteries. Micro fuel cell is, it's kind of a you know the fuel cell, but it will be in a miniature size. Something it will use biological components as fuel, like bacteria or some other lactate can be used as an fuel to power this some of the devices. And micro heat engines and super capacitor, you know. So it's kind of a capacitor, but it can able to have can able to store the more energy, and it can able to release the more power instantaneously. So these are the things, the basic power sources. Okay, and how the power, because we know the power source, but everything we need to measure it, right? Without measurement, then we can't able to design. So let me say take iMode 2, that average power is 12 milliwatt, peak power is 170 milliwatt, and communication during communication is 141 milliwatt, and processing requires around 99 to 170 milliwatt. Let's say we can able to make a Echo B, Apple Watch, Samsung Gear Fit, everything we can able to know that. So if you design anything, if you're if you're selecting any components or any communication protocol or a microcontroller, you should know what is that average power, because this components includes our microcontroller, sensor, actuators, and RF communication device, right? So otherwise any interface for users, all those things we need to know. What is the average power, what is the peak power, what is the power it is going to consume during communication, what is the processing power, right? This is the power demands for commercial IoT networks. Okay, now if you, though we have these are the energy capacity and power capacity for different energy sources. Let's say if you use primary battery, lithium coin cell, it is 110 milliwatt per centimeter cube. You can able to have this power source, and the energy is 670 milliwatt hour per centimeter cube. And what is that power per centimeter cube year? So it can able to last for 0.076. That is the power per centimeter cube per year. And secondary storage, no. And commercial availability, yes. And you know this, our primary cell battery, we have to use in our CMOS battery, right? That is a primary coin cell battery. And it is inexpensive, no need of voltage regulation. And if you have the primary battery, alkaline AA battery, it is 200, and it is different. You can see different types of power density, energy density, and what is the year it can able to serve. And the storage, no, because what is the secondary storage is kind of you need to have any supporting is required or not, because some of the things, micro fuel cell, micro heat engine, and super capacitor, dedicated RF, all those things we can't able to, and even solar outdoors, indoors, we can't able to completely we can't reliable on them, right? So always it needs some secondary storage. If you see our lithium coin or primary alkaline or secondary battery, it does not need any secondary storage. And the micro fuel cell, so it is having low efficiency, and again the fuel storage and delivery challenges there, but it is not commercially available. And micro heat engines, it is not commercially available. And super capacitor is available, but is become limited density and self discharge. You know, this capacitor will have this leakage resistance, it will have self discharge. And dedicated RF, yes, it is commercial, but it is expensive, limited by range, requires AC input for the RF source. Again, solar in outdoors, solar intermittency, because we don't get always continuous solar light. And indoors, again, it is going to be expensive one. So these are the comparison of different power sources. What is the power density, energy density, and with some pros and cons. And again, if you want to harvest, right, you want to harvest from airflow or water flow, or with temperature gradient, or for mechanical force, like temperature gradient is like our, we can know thermophile, or we know the Peltier heater, right? So inverse of a Peltier heater, we can able to use this. And mechanical, piezoelectric, or triboelectric, by with some friction, or by mechanical, or by movement, whether we can able to make all those things given. But you can say most of the things are not commercially available, and it is always say it is unpredictable in nature, right? So the power harvesting, always we can say it is very difficult for IoT device to have it. Okay, so these are some of the practical examples. I took it from one paper. So this powering environmental internet things I have done. So they kept solar cell here, and this complete IoT device is powered by the solar cell. So what are the advantages? So it is, until it is our microcontroller works, our communication works, it can able to power it. And if you want, you can able to have any secondary storage for battery, right? Whenever the daytime, the solar will get power, and it can able to store the energy in that. And if you see the thermoelectric generator system, this is a typical schematic diagram. So if you take any Peltier heater, if you can use it as inverse, you can able to heat it in one side and cool it on another side. You can able to produce any EMF across it. So you can use an energy harvesting device. And simple horizontal airflow energy harvester. So in this, we have the cantilever beam.
Excuse me, Ishwarmurthy garu, slide complete ga screen కనిపించట్లేదు. Slide mode లో లేనట్టుంది.
Sir, it is I can able to see complete screen, sir.
మాకు visibility slide show లో కనిపించట్లేదు.
Just a minute, sir. Just a minute.
Okay.
Otherwise, I need to. So now it is okay.
Right. Now it is okay, sir.
Okay, sir. So we have this magnets, and this is a cantilever beam. So according to the airflow, this coil will move across this magnets. So it can able to, according to the Faraday's induction law, it can able to produce some power. So these are some of the things. And this is a triboelectric nano generator by harvesting ambient mechanical energy. So somebody is carrying back. So it is moves here as it is moves. Well, movement, it will have some movement across different elements, so it can able to produce some of some energy. So these are the things in research, not yet in available in the commercial. Then what are the considerations for energy harvesting? What are the considerations? One is monetary cost. What is the cost is required, and storage energy is required or not, because we can't depend upon the only for energy harvesting, how it is the storage required or not, and environmental compatibility. Let's say some of the things, let's say for our solar cell cannot be used in the dark environment, and our solar cell cannot be used in where the sunlight is very low, right? So some of the things cannot be worked in higher temperature. Some of the things can't work in lower temperature. Let's say if you take the Peltier heater, if you want to put it in some lower temperature area, then we need to maintain the gradient temperature. Then according to the gradient temperature, you're going to get the power. So that is not possible with the Peltier type of energy harvesting. And one more thing is efficiency. Let's say if it is less efficient, then you have to increase the surface area. You have to put lots of energy harvesting devices to get this energy. And what is the energy output? Whether energy output is sufficient to cater the needs of the particular IoT device, whether it's a sensor and communication network actuators, and what is the space available. You can't have, we can't have the larger area to deploy the IoT device. So this all those things we need to consider before the harvesting. So considering this, harvesting is feasible, but only thing is it's not yet established, right? So our currently our IoT device can operate very happily in battery or in mains power supply. So because the IoT, there is no chip, or there is the people are designing for the chip where it can able to consume at least milliwatt of nanowatt of energy continuously, right? So this harvesting system can't able to deliver continuously all those powers. And whatever the design the people are making in IC or VLSI technology, they are not going to consider only VLS for IoT application. They will consider the device has to work in the for general purpose also. So one option is we can go for the battery, right? So battery is the main thing we need to know how it is can be used for IoT. So it is again, it is not only the single battery. Let's say our AA or coin type battery, we can use it. We can able to deliver. We can able to get the power from the battery to use our IoT system, to use for the IoT system. So we need to know what are the types of battery and how it can be used. We'll see. So the people used to the common name called CR, BR, ML, right? So these are common type for coin, and AA. Lithium or alkaline, we can able to say cylindrical, and lithium thionyl chloride is a coin and cylindrical type, and solid state thin film is thin film and planar. So then we have different anode and cathode materials, and rechargeable. Some of the things are rechargeable, some of the things cannot be rechargeable. So rechargeable they called as an primary, and with the batteries cannot be not reachable, can be taken as a secondary batteries. And for each battery will have the nominal voltage, right? So for CR, if you take our CR battery, we used in CMOS is a 3 volt. And if you say our alkaline batteries, we can use it in a remote, that is a 1.5 volt. and lithium same cylindrical FR6 type is going to give 1.5 volt. Lithium ion cylindrical is going to give 3.6. So lithium cylindrical or the pouch type where we can use it in our cell phones. It's kind of pouch type. So it's giving 3.6 volt. So these are the things. Again, we should know what is the standard continuous load rating, right? So C by 100. So what is the C? C is, let's say the battery is 1000 milliampere. If battery is 1000 milliampere, what is that standard loaded rating? Let's say if it is 1000 milliampere, that is the C. That is the C. So 1000 milliampere by 100, you can able to take 10 milliampere, right? So if your battery, CR battery is 1000 milliampere, for example, I'm saying 1000 milliampere, you can able to continuously load that battery with C by 100. That is, C is the capacity we call. So we know our cell phone battery is 2500 milliampere hour or 3600 milliampere hour. That's the capacity. Let's say the what is, then again you should know what is the continuous loading rate. So this by C by 100 is, so 2500 divided by 100. So it will gives 25 milliampere hour. So like this we need to, again BR battery is divided by 1000, and if you say ML type is divided by 300. And for some lithium cylindrical, it is 1C. If it is a lithium, let's say 200 milliampere, 2500 milliampere per hour, you can say 2000 milliampere at you can able to draw from that, right? And lithium thionyl chloride is C by 10,000 times, and solid states 2C, right? Twice the capacity you can able to withdraw the current. And again, this depends upon this, the self life and operating life in the years they given. Let's say if you take CR, it is about 10 years, and if you see our lithium thionyl chloride is about 20 plus years, and the different operating range you given, they're given here. So accordingly, we have to choose our battery, and according to application, we have to choose our battery. So these are the different comparison between the batteries. Okay. Then we should know how this discharge characteristics looks like. Let's say this discharge capacity is a function of discharge rate, right? Discharge rate. Let's say you have a battery, you are going to discharge at very low current. You can see the first graph. This, let's say we can take manufacturer 2, this blue color, right? This blue color, the user is going to discharge with only 15 milliampere. So the capacity we can say around it is 3100 milliampere hour. But same user for some other application, it is going to discharge for 100 milliampere. Then this capacity is decreased 250 milliampere hour. Milliampere hour. So it is keep on, if your discharging current is increased, your capacity is going to decreasing, right? So it is not like that kind of a tank. If you take 1 milliampere per, let's say if you are taking 1 milliampere and it was to, let's say battery capacity is 1000 milliampere hour. You are drawing only 1 milliampere. It is not that the battery has to stay long for 1000 milliampere. If you take 100, the battery has to stay for 10 hours, right? It is not like that. So if you keep on taking the increase the current from the battery, this capacity will decrease. So again, this capacity is depends upon the manufacturer, and they have measured this one for 0.5 gate cutoff voltage, right? Because default it is around, if you measure any of the alkaline battery without load, with fresh battery, it always give 1.6 to 1.7. So if you keep on drawing the current, if you discharge below is 1 volt, we can say it is unusable one. So again, how is the voltage drop, right? How is the voltage drop? Let's say here, again, 2 manufacturers they took. So manufacturer 1, blue manufacturer 1, this time they took it for red color again. So if you take a blue color manufacturer 2, let's say you are discharging this continuous line, if you are discharging from 1 to 0.8, right? 1 to 0.8 volt. So here, if you discharge for, if you are taking 100 milliamp, 10 milliampere, the capacity is 300. And again, if you discharge at around 700, then capacity is 150, 1500 milliampere hour. And the same thing, if you are decreasing 1 to 1 volt, right? So then it is very, the capacity is very less. The capacity is very less. So up to 1 volt means it is the, you are going to have the very less capacity. It can reach very rich. And if you want to make up to 1.2, then the capacity is again decreased, right? So let's say some of the microcontroller, we can say that it won't operate for below particular voltage, right? So if it is if it can able to operate at 0.8, the capacity of the battery can be, we can say it's around 200 2000 milliampere. If the microcontroller going to operate up to 1.2, then you can utilize only the 500, because below 500 milliampere we are going to not it is unusable, the battery, right? So it is depends upon where you are going to stop the voltage. So here they given here again battery type, and the common type is CRML, and depiction is this coin type. And what are the storage capacity of the CRML? It is from 1 milliampere to 1000 milliampere hour, and typical discharge is C by 100, and the discharge voltage is 1.5 to 3.3. Again, cylindrical lithium ion alkaline thing, that is a common name is 18650 AAA. So the storage capacity is 225 to 5000, and the typical discharge is C by 10 by to C by 2. So here the typical discharge rate is that, so it is able to discharge, can able to discharge 100 milliampere hour. Let's say if you are discharging 100 milliampere, the battery is going to last for 1 hour. That is a theoretical thing. But however, you have to follow the typical discharge rate, right? And the parasitic prismatic lithium ion is 9 volt. It can able to discharge up about C by 10 and C by 2. It can able to have up to 2000 milliampere hour. So these are the different types of battery. And if you see our lithium polymer batteries, you can able to recharge up to 1 C. Let's say if it is lithium polymer batteries for 500 milliampere hour, then you can able to drop 500 milliampere. It is not like the divided by 10, right? And solid state film, it is to 20 milliampere hour. You can able to withdraw 40 milliampere because it's 2C. And these are the different voltage ranges. Again, they given energy capacity and energy density, right? So energy density is, what is the energy density per centimeter cube, and what is the capacity, right? So if you say BR2032, for example, it is less than, we already seen it is between 1 to 1000, right? If you see around 50 or 100 typical capacity milliampere hour capacity, here this energy density is around 500 milliampere hour per centimeter cube. That is energy density, because for developing any IoT device, our size matters, right? Our size of the device matters, size of the battery matters. So here, this is the energy, this is the typical capacity, but energy density of the battery, this is the size. Now this is the thing. Let's say the energy density should be more. If energy density more, within small size, we can able to store the more energy. But if you take VL621, you can see, right? Per here is very around almost it is equal to 1 or 2 milliampere hour, and energy density is less than around 25 1 milliampere per centi cube. centimeter cube. But however, you can say AAA alkaline, your typical density is around 2000, but the energy density is around 600 milliampere per centimeter cube, right? So if you keep on energy density is more, you can able to get this in less decrease in size you can able to achieve. Again, this battery discharge capacity as a function of discharge rate. So let's say you are discharging very fast, then your capacity will decrease, right? If you are 1 by C rate by hours, so if you are, this is a 1 by C rate, at 10 by C rate, at 100 by C, this is a differences. So if you keep on decreasing this, if you are decreasing the increasing the discharge rate, again this discharge capacity also decreased. Let's say some of the batteries, it is you can able to discharge complete 100%, right? Some of the batteries, if you discharge very at high, then you can able to see only the 60% you can able to discharge. So these are different types of batteries. These are different types of the ratings. Let's say it is not like that. The battery cannot be used. It's 100 milliamp 3 volt 3.3 100,000 milliampere hour battery cannot able to deliver complete power. It is completely dependent upon the discharge rate. Here also, how this battery discharge capacity is a function of discharge rate. This is discharge capacity, and if it is keeping discharge increased and discharge capacity decreases. Some of the batteries ML12220 coin battery from 0.01 to 1 milliampere, it is common. But some of the things you can see discharge, if you keep on increase the discharge current, discharge capacity is decreasing. Again, temperature also matters because it is completely electrochemical process. So electrochemical process, the temperature is the main component to play the role in oxidation and redox process. So how this temperature? Let's say for this AA battery, let's say with the thick line. So at 20 degrees Celsius, we can able to use normalized capacity around 70%, right? So here this dot is CR2032. At 0 degree, you can able to 100, but keep on increase the temperature. This capacity is decreasing. The normalized discharge capacity is decreasing. So this is because while selecting the battery, you should know where our IoT device is going to deploy. That is also important. Again, this is the battery voltage during discharge for various chemistries. So we know the alkaline and thiol chloride, lithium ion, and solid state lithium and micro battery. How the voltages? Because it is not like that. Our battery is 3.3 100 milliampere per hour. It is does not guarantee is going to give 3.3 voltage until you drain the complete battery, right? So how the voltage decreases? Because some of the applications we need constant voltage. Otherwise, what do we need to make the constant voltage? We need to have another DC to DC converter to make the constant voltage, because battery voltage is not always constant, right? So how the voltage is for different chemistry? At 0% discharge capacity, it is maximum. You keep on decreasing, you keep on discharging, then how the voltage decreases for different chemistry is given in this graph. So again, cell resistance. So for every DC source or every source, we will have the internal resistance, right? So when it's battery's state of charge, what is the state of charge means? What the charge stores in the battery. So let's say it is 100%. Then we can say it is around, the cell resistance is very less, around 1 ohm, but it is completely discharged. You can say it is cell resistance drastically increased, right? So this is the way the cell resistance, because if keep on after 20, let's say after 20 we keep on increasing the if you're drawing the current, we can say most of the current is dissipated in the battery itself as in the internal resistance. Okay. Again, the price also we should know, right? The price also we should know. For battery, let's say BR 2032, what is the typical capacity? It is 190 milliampere rechargeable. What is the price and what is the price per milliampere hour? So given the comparison, because for after making the bills of material, we need to check what is the cost, right? So for this required one, whether rechargeable required or not, right? By some other means you can able to harvest some energy. You want to recharge the battery, then accordingly you have to select this batteries. Then battery price comparison. We can say this is BR 202, this is the value, and battery price per energy. So the battery price per energy should be less, right? Then only it is feasible for us. So it is given in reverse actually. Dollar one, let's say $1 for how many milliampere car. So it should be inversely should be high actually. Again, life cycle, right? So if you use a rechargeable thing, how the capacity? Hope in practically we can able to experience this when our new mobile used to give for a long time. Yes, lifetime goes as it is lifetime decreases. So we should know what is the life cycle characteristics of the particular battery. Let's say you keep on charging, discharging in this battery. After 500 cycles, this capacity is decreased from 2750 to around 2250 milliampere, right? So for choosing before buying a battery, you should know what is that temperature range can be worked on, what is it, which temperature it can able to give maximum capacity, and for after some type of cycles, how many number of cycles it is going to have less capacity. So all those things we should know. Right? So again, we should know what are the different types of holders we can use it. So AAA holder, and for lithium ion 16656 holder, and we know that 9-volt battery holder, and it is kind of an coin holder, right? So these are the different types of holders we can able to have it in our IoT device to hold our battery. Okay. Now we have seen the battery. Again, we need to some kind of optimization we have to do, right? So in IoT device, some device has to sample for even for 1 second, some device has to sample for 1 minute, some device 1 hour, some device even 1 day once, right? So sampling won't be same for even the same application, right? So for if you want to measure the temperature in the room, right? So it is no need to be sampled for every seconds, because if you want to change the temperature of our AC, you can do it for even 1 minute sampling is okay for that. But if you want to do it, your system, IoT system, going to give some input to your any control system, so the sampling should be very high, and you are going to deploy the sensors in forest to detect any wind velocity, all those things, right? Or measuring the temperature, or all those things. Then according to the sampling rate, we can able to change it. So remaining things, we know we have the option in microcontroller and so many sensors and actuators. We can put them into the sleep, right? So put them into the sleep, and whenever by giving a software interrupt or hardware interrupt, we can able to wake up and it can able to do its function. So again, we have the each device sleep mode is different. So some device in sleep mode can able to access some of the parts. Some device, if it goes to sleep mode, we can't able to access this device. So all those things. So what is the, but then how to calculate the what is the average power? The average power, we know that the P sleep, the power utilized in the sleep, and the percentage of time sleep plus P active into percentage of time active divided by 100. This is the how we can able to have this. We can able to calculate the P average. And here we can able to let's say in this if you see, we have the microcontroller, and some of the devices. We can able to give this some request so to I2C. So if we give this IRQ2, can able to switch on the power of this microcontroller. If it is on, this is able to power the microcontroller and sensor switch, right? So like this, we can able to make excuse me, we can able to make our device to sleep mode, and we can able to make only by directly connecting the power. Another is only to by using I2C. Another is by using interrupt, right? This is it's kind of a sending command to I2C from CBC 34803. This is completely controlling the power itself, and this is by giving some interrupt, right? Some hardware interrupt. So like this, we can able to have this. We can able to make the microcontroller some other device in sleep mode, again back to the wake mode. Here we can see what is the power savings. What are the power savings, and we can able to achieve. So this is sleep current is 0.6 microampere, and per megahertz. This is a cycle. This is a 1 megahertz. Let's say the cycle, and the active runtime is 0.1, and the sleep time period is 60 milliseconds, and the active current when running is 200, and the active time per sleep time is 0.063, and number of instructions is 100. The power saving ratio we can able to say 0.47, right? So it is not like that. If you do on and off, making the sleep and waking up, it is not always going to save the power, right? It is not always going to save the power. Sometimes it while waking up, it has to insulate some of the peripherals. Otherwise, it has to insulate some of the codes. Otherwise, it has to insulate some of the communication protocols, right? So at that time, it has to run more number of cycles, and more number of cycles means it is more number of instructions you has to run, and it will take more power also, right? So it is depends upon your system when how much time you can able to put it in the active mode, and how much time you can put it in the sleep mode. And as soon as from the sleep in active mode, what are the things it has to do, right? It is not like that. As soon as come from the sleep, it can't be in. It cannot be inactive. It has to do something. It has to check its hardware, or some of the things it has to check. Then how it can be possible, and how much time it should be in active, and how much in sleep. Accordingly, you have to do it. Right. So some of the things you can able to achieve 6.3 ratio of the power saving also. So this is the basic block diagram. There's some sensor node can able to incorporate the energy harvesting module. So we have the sensors and MCU plus radio, and we have the data out. We can say this is a typical IoT device, right? Sensor plus MCU plus radio is a typical IoT device. But if you have any energy harvesting module, then you should have energy harvesting transducers, and you have the energy converters and energy storage. Because here energy transducers may be RF, or it may be the thermopile, or it may be the solar cell. After that, the energy has to be converted, because it is the energy is not be stable one, but our sensor and energy MCU needs always a constant voltage, and it has to have, it can able to have withdraw some amount of current from, or we can able to withdraw some power from this energy source. So we should have energy converter as well as the energy storage. So if we use less than what are the devices typically suitable powered by energy harvesting sources? The RTC, real-time clock, less than 100 nanowatt. The MCU standby, less than 1 microwatt. Watch or calculator, less than 100 microwatt. RFID tag, less than 100 microwatt. Sensors, less than 1 milliwatt. Wireless sensors, 10 milliwatt. Bluetooth transmitter, less than 100 milliwatt. GPS, less than 1 watt. Mobile phone, less than 10 watt, right? So accordingly, you have to choose the power harvesting technology, right? So we should know what are the applications and what is that average power, and from that only we can able to choose the energy harvesting. Let's say if you think that our piezoelectric element, whenever we give the mechanical pressure, is going to give some power. If you consider like that, then we have to place to operate a GPS. It requires around 1 meter cube of area, right? So we have to think what is the energy required and what is the suitable power harvesting and what is the energy storage for that also. Here, what is the conventional energy harvesting transducer and characteristics challenges? It is present to the designers. So here is the light. So conform to small surface area and wide input range. That is the thing. Because if the light is low, our solar cell is going to give less voltage, and light is high, then light intensity is high, then is going to give more voltage. So the wide input voltage ranges are there. Again, this input resistance also varies, and typical voltage also varies, and typical power output is 10 microwatt to 50 milliwatt, and the normalized cost is $0.5 to $10. Again, the vibration kind of piezoelectric, it is again also the typical impedance between kilo ohm to 100 kilo ohm. So the AC voltage will get 1 microwatt to 220 milliwatt, and the thermal gradients, the efficient heat sinking, so it has 1 ohm to 100. Again, we have typical voltage. Voltage is 10 millivolt to 10 volt, and typical power output is 0.5 to 10 milliwatt. And RF and inductive coupling, these challenges the coupling and rectification, and the constant impedance is lower than around kilo ohms, and is a very distance, right? We know this, the RF and inductive coupling can be vary with the distance, then it should be used, and typical power output is wide, and normalized cost is 0.5 to $25. So again, we need to again the maximum power transfer theorem. So how should be the R load and R source? So we accordingly we have to choose the R source. Before that, we should know what is the R source. Whatever the source we are using, we should know what is the R load, and accordingly we have to be able to draw the more power from the source. Okay. Now coming to the depth of discharge, this is also important. So what is the percentage of battery we can able to use it, right? Let's say Tesla holds 13.5 kilowatt hours, and they're going to say you can, the depth of discharge is 96%. So we can able to use 13 kilowatt hour energy from that, right? Right? If some manufacturer going to supply 10 kilowatt battery and recommends depth of discharge is 80%, then we can able to use only 8 kilowatt, right? So it is depends upon the battery manufacturer and what is the technology they are using their battery. Let's say, but nowadays their batteries are 100%, they're saying, but it's very difficult to achieve. Let's say what is then how to convert the battery into power? We know let's say for example 2000 milliampere hour. It is going to, with nominal voltage is 3.3. What is the power? 3.3 into 2000 milliampere hour. It's give 6.6 into 1000 milliampere watt. Sorry, it is going to milliwatt hour, right? That is milliwatt hour. So sorry, watt hour, because we have 2000, right? It is watt hour. So it is not like that you are going to take power, you can't able to take all those 6.6 watt hour from the battery. It is depends upon the DOD of the particular battery. If manufacturer mentions it is 80%, then you can able to consume the energy around 80% of stored energy in the battery. If it is mentioned it is 96, you can able to consume the 96 of stored energy from the battery, right? And again this is also important. Let's say you have the battery charging, you have the battery charged at 90% and discharging up to charged at 100, discharging to 90, again charging 100, discharging 90. Then the battery can able to last for 15,000 cycles, right? But the same battery you are charging from charge to 100, again discharge to 20, charge to 100, discharge to 20, then it can able to last around 30 cycles. This 100 is capacity, right? So only 3000 cycles, right? So that's also matters. How it is going to charge and discharge in the battery. Again, it is a idealized some of the operating life of the continuously of different batteries. Let's say for example, we are going to say take 50 milliampere hour solid state battery. One is blue is average power is 1 microwatt. Then it can able to withstand 20 years. The average power, another is average power is 100 microwatt, right? Then we're going to withstand less than around 2 years, right? So like this, this battery life, it won't be like it's kind of a proportional. So these are the different types of battery. Then how your average power decrease the lifetime of the battery, right? Or is going to the depth of discharge is around 100%, or is going to discharge completely. So these are different types of batteries, and how this average current, average power consumption can able to have this battery. We'll have this battery capacity, right? And again, here we can see some 500 milliampere solid state battery. You are going to discharge 80%. Let's say 100 to 20, 100 to 20, like this, charging up to 100, again discharging to 20. Then this, if your power is 1 microwatt, then the lifetime is only around 100 years, right? But it is 100 milliwatt, the lifetime is only 1 year, right? So if you are, it is only 1 year. And the same thing, if it is say 70 milliampere hour kind battery, you do it for only 10% of DOD. Then if you take in 1 milliampere hour, the battery life is around, let's say 600, 700 years. And if you take same 100 microwatt hour, it is going to be around 1.5 years only. So these are the things. So that's why we should not allow our mobile battery or laptop battery is completely drain off. At least we have to charge as soon as it reaches 70, discharge to 100%. Like this, we have to do it. So again, these are the some of the energy harvesting technology, and what are the possibilities and futures can be done with this, right? For home thermostat, the future should be wireless Bluetooth radio. We can use solar, right? For any medical patch, right? We want to send any temperature from a medical patch, all those things. The features should be temperature, pulse rate monitors, NFC communications, and it can be solar or electromagnetic. These are some of the things they're given for different applications like wireless parking meter, smart indoor, factory automations. All those things are given here. And here again, we know that in flight, they won't allow battery to be in check-in packages because due to safety. Because in Airbus, some of the lithium-ion battery was best out, it will lead to accidents. So there are some standards we need to follow. Whether the battery, where the battery can be deployed, and any transportation can be done in that battery, right? So we have any battery, all those things you have to follow some standards. The American National Standard Institute, they'll have ANSY's C118.1M is for portable battery cells, cell aqueous solution. So we have to check that particular battery standard, battery safety and transportation standard to deploy any before to our device, right? So we should, because some of these things need to be followed. Because we need to go for any, we need to sell our products, right? So we need to say these are the things we followed, and some quality checks are necessary for this, for use a particular battery for particular application, and how this application is going to behave in future. So until now, we have seen this batteries things. So we have seen what are the harvesting thing and the energy capacity and power capacity of the harvesting thing. And we came to know that harvesting is possible, but however, it need energy, separate energy storage. And we came to see the batteries, different types of batteries, and how their discharge capacity vary with discharge current, temperature, and DOD, right? So many parameters we have seen, and how this voltage drop across with the different voltage current, all those things we have seen. So we have to choose the battery. Before choosing the battery, we need to consider all those things, right? Okay. Now, while designing IoT, we'll miss some of the things, packaging, right? We will miss packaging. Here we can say one is PCB package. Here we can see B is a system in package, and C is system on board package. We'll see difference between these three different types of packages. So we'll know how normal by using dual inline package ICs. We used to solder and we'll develop a battery, all those things. That is a we'll buy the different components for each application that will make some more PCB. And system in packages is kind of an node MCU, all those things are. We will have the, or some of the microcontroller will have inbuilt Bluetooth protocol, right? Instead of soldering or connecting one more Bluetooth devices, we can have the microcontroller with inbuilt protocol, Bluetooth or inbuilt Wi-Fi. All those things were possible. That is a system in package. Some of the system on board is, let's say, it mostly used in wearables and satellite applications or aerospace, because you can see our IC, though look like, let's say if you take 741, it has 8 pins, but inside will have micrometer size of die inside, the semiconductor piece inside. Only thing is for making the connection out, we are making all these wires. So what will they do in system on board? They'll take only the particular die. Before packaging, they'll put it in some device and they will make their own devices, right? So they will make 2 or 3 dies like that. They will interconnect each other to in that particular packaging itself. They will give a they can able to make a new device. That is a system on board. So these are different types of thing we'll have. So multi-chip integration, single chip application integration, we can see later. So this is a general packaging trends. So we can say it is from TO can type, right? We nowadays even some BJT transfer used to see in that CAN type, and deep we have SOC, we have PQF, we have PGA, CSP, WLP. Are those things are different general packaging trends. And the same thing, we have the MEMS. So micro ultra mechanical system packaging also came like this, like traditional packaging and capped molded packaging, no cap in injection mold packaging. So all those things leads to the miniaturization. These are different types of the packaging trends in both the general packaging trends and MEMS packaging trends. So it is not necessary, because again the selection of microcontroller, right? That's also important. Not necessary we have to use any PIC or 8051 ARM controller and with any Bluetooth module to have some IoT application. We should know how many GPIO pins needed. Otherwise, what is the number of pins needed for in future, right? All those things we should able to consider. Then accordingly, we have to choose the microcontroller, right? If you see C251 simpling, it is a Bluetooth low energy proprietary wireless MCU. It has some basic input output port. So no need to buy microcontroller, Bluetooth module, all those things. You can have both the devices together, and you can able to operate with that. So these are not required actually. So these are interconnects, all those things. This. Yes, you can see how this devices are made. You can see this is a LDR, and it has some two boards, right? Like this they are made, and it's kind of the 3D PCB assembly, right? The 3D PCB assembly they made, and they can able to make it. And it is a very compact. Same LDR is placed here, but is a compact PCB level wireless sensor network. So these are different things we can able to achieve. It is where we are going to deploy it and how it can be used the system. So how this Nexus 7 tablet computer, individual chip, and all those things that are used here. So these are too much packaging. You can do this. Again, how this RFID, right? So from RFID or for antenna patch, how we can able to harvest the power, right? We have antenna coil, and we can able to paste, and how to we can able to harvest the power. So these are the different PCB board, and we have the cantilever, different cantilever, and we'll have the PSD patterns, right? This is a piezoelectric. Whenever there is any mechanical movement, it can able to generate the power harvesting. So these are some of the things. So again, we have the camera, and the camera core with electronics and sometimes IR links, detector, uncooled focal plane array, and the pixel, each sensor retina thousands of pixels. So it is not like that you have to buy the camera itself. You can able to buy the pixel. If you are able to integrate with a detector or some of the core, it is possible, right? So it is not like that you need to buy the camera for any applications. It depends upon that to miniaturize the size or to have the less power consumption. Accordingly, how to do it. Same thing. What are the things for component level packaging for even for small camera? Right. Okay. So these are the things. Only thing is we need to know what is the power supply and how this can be packaged. And coming to the communication protocol, hope everyone knows, but I think the Arduino and some of the libraries, they spoil the student ability to think about how it works in background, right? So the thinking, connecting two devices and getting the data from the two devices is not a thing, but student has to know what are the things running behind it, how the data frames are communicated between the two devices. Let's say everyone know about the UART, Universal Asynchronous Receiver Transmitter. So it is kind of a serial port, and it doesn't have any clock. So any UART 1 and UART 2 has to be connected TX to RX and RX to TX. So TX to RX and RX to TX and ground. Then the number of wires is used to, and maximum speed is 1,15,200 baud rate, and it is usually 9,600 baud rate. And synchronous, it is asynchronous type, and serial or parallel serial type. Number of masters and number of slaves can be one, right? The baud rate is number of bits can be transmitted per second. How the data frame, because we should know how the data frame looks like. And we have the one start bit, and data frame is again 5 to 9 data bits, and again parity bits to check check for any errors, and we have the 1 to 2 stop bits. So the start bit always will be low, and we have the data bit, and parity bit we'll see, and stop bit also is become too low. So the parity bit is high when number of ones in the data is odd, and same parity bit is low when number of ones in data is even. Here we can see how the transmitting is going to happen. So for transmitting, it has to start with, it has to make 0, right? Start bit, this 0 is become, and again 0. Then we have to transmit the data 0, 1, 0, 0, 1, 1, 0, 1. After that, we have the parity. It depends on the number of ones and zeros, then become 0, and stop bit is become 1. Like this, data frames are sent between the two devices. Advantages: only 2 wires, and no clock signal is necessary, and the parity bit is allowed to error checking. The structure is data packet can be changed. So only thing is, instead of 9-bit data, you can able to make it 15-bit also. But only thing is, both sides you have to change. It is well documented and widely used one. Again, disadvantage is maximum size is 9-bit and does not support multiple slave or multiple master, because it is kind of peer-to-peer communication. It is won't support. And baud rate is this is only 10% of each other. Let's say two devices want to communicate with 9,600 baud rate. Let's say due to the microprocessor for both the any one of the things is the clock cycle is decreased, then the communication is possible, not possible. At mega you have. Again for UART, this voltage levels are different in TTL as well as R232, right? So TTL low is equal to 0 and high is equal to 5 volt. But RS232, if you take your system, you know, D9 pin serial port. In the serial port, low is plus 3 volt to 15 volt. High is minus 3 volt to minus 15 volt. Then if you want to communicate TTL logic to RS232 logic, then you have to use some max 232 IC. By using capacitors, you can able to make it. So nowadays, Arduino is coming with direct way. So application is the PLCs, variable frequency drives, servo drives, and computer CNC machines, right? And moreover, it is being a peer-to-peer simple in communications. Nowadays, these adapters are being used in the personal computer. So main disadvantages is large voltage swings in RS232 plus 3 to minus 32 or minus 15, right? So any device can't able to reach +2 minus let's say -3 to +15, right? +15 is 0 time. It needs some rise time, right? So large voltage swings, then you have the large power, and it takes time also. So it is going to decrease the speed, and it is being a single-ended, right? It is going to communicate with single-ended, and it is having prone to the electromagnetic interference, right? So it is prone to the electromagnetic interference, and with this we can't able to make. With this we can't able to make connect two devices, multi-drop we can because only thing is 1-to-1 we can able to make, right? So for this only we came to the differential signaling. We came to the differential signaling. Here, if you consider differential signaling, we'll have input pulse, and you'll have the input pulse. One pulse is going to high, another pulse is coming 0 to minus. So if you subtract both the things, you'll get output pulse. Let's say both pulses are get disturbed by any noise, right? Then if you have the subtractor, then you will get same output without having the noise, right? That's why more nowadays RS432, RS485, Ethernet over twisted pair, PCI Express, DisplayPort, HDMI, USB, everything is a differential signaling instead of single-ended. So though the RS432, RS422, RS485 uses kind of an UART, but mode of operation is single-ended, is differential, and number of drivers and receivers per one line is one driver, one receiver is one driver, 10 receiver, and the maximum cable length is 50 feet, there is 4,000 feet, and maximum data rate is 1,600 kilobits, 10 megabits and 10 megabits, right? So why this cable length is decreased? Because our cable is not only the just a conductor. It will have this parasitic capacitance. It will have resistance, and it will have inductance. Let's say if you keep on increasing this length, what is going to happen? It is going to increase the capacitance. If it is capacitance more, we know the RC will be there and the rise time will be more, right? That's why it is a very difficult to have. Again, same thing, RS 485 bus, we'll have this some software must be run on this one transmitter end, because though you are using 482, 485 as UART, but with help of software we can able to have one slave and multiple one master and multiple slaves. And we have the SPA. We have this synchronous serial data transfer protocol named by Motorola. It is a full duplex. So at a time, the master and slave communicate each other. So it is using 4 wires, and maximum speed is 10 Mbps. It is synchronous and serial mode, and number of master is 1, theoretically unlimited. So how it is going to conduct? So master device has to initiate the connection and control it, and master and one more slave can transmit and receive the data. And it is mentioned earlier, master can send the data to the slave as well as slaves can send data to the master same time. So if you take any pin out of SPA, we have master output, slave input, master input, slave output. We have the clock and the chip select, right? To chip select is the master has to select which chip or which slave has to get the information or which slave has to transmit the information. So again, what is the purpose of clock? Because the clock used to sync the both master and slave when to sample the data. Here, let's say here sampling data can be rising edge or falling edge or high. So let's say here rising edge. So data is here. So whenever the falling edge is there, so at here first bit is 0th bit is 1, again first bit is 1, second bit is 0, third bit is 0, fourth bit is 1. Like this, we can able to have it. We are able to sample the data. So receiving also same thing. Whenever the clock cells goes to at a rising edge, we need to sample it. Here everything is pre-arranged. Both the devices has to know when to sample, right? And how many bits, all those things. Everything is pre-arranged here. Here we need to select the slave. We need to select the slave. So which slave? Because we're not going to pass any address. We are not going to pass any address. So we want to send a particular data, or we want a particular data need to be accessed from a slave. We need to select only particular slave. Maybe slave select can be maybe 0. Pin can be make it to low to select it. So these are the things. First is we need to start the clock. Then we need to start the slave select. We need to be 0. Then we need to send this data to master output slave input. Otherwise, the slave also can send to the master input to slave output. Accordingly, this is the process involved. So this is the process we can able to have this slave 1, slave 2, slave 1 by using this slave chip select or slave select. We can able to access multiple slaves. Only thing is the master should have enough GPIO pins to control all the slaves. So this is for when getting data from sensors, it has to be every sensor has to be get this from sensor. But if you want to send any data to LED, right? We are going to send the data to LED, and data to LED, we are not going to receive the data. So this is kind of a round robin we can able to make it. So the data can be sent, and accordingly we can select the chips, then you can transmit the data, right? So that is possible in this. So we have the Arduino programming, all those things we have. Distance is being a high speed, it can be transmitted to the short distance. Because again, the wide is, we know our wire is not only a pure conductor. It will have this R and C. The signal integrity would be maintained in the communication. So that is the problem in this. Advantages: fast and asynchronous, simple shift register can be used, and supports multi-slaves, and no start and start bits, higher data transfer rate than I2C, and it is a duplex mode. Disadvantages: more signal is required, and communication need to be well defined before, and the separate SS lines to be needed, and there is no form of error checking, and single master, no acknowledgement. So they came up with, they took advantages of VWAT, they took advantages of SPA, they came up with the I2C. It is by flips. So it can able to do the multiple slaves with the single master, multiple master control the single multiple slaves, and one microcontroller. All those things can be possible with I2C. So in this we have serial data and serial clock, right? Hope everyone knows if you take any devices. So again, how it can be transmitted, the number of wires is 2, and maximum speed is 100 kbps, fast mode is 400 kbps, high speed is 3.0 mbps, ultra fast 5 mbps. Synchronous, serial, master is unlimited, but slaves is 1008. Here they are going to combining the data of both SP and UART. So it have this start bit, and it have address frame, and it have read or write, and it has to get acknowledgement or no acknowledgement, and again it transfer the data, again acknowledgement, no acknowledgement, again data, no acknowledgement, no acknowledgement, stop, right? So the start condition is, let's say one master has to start the conditions, and it has to send the address, right? Address to all the slaves. Then it has to say he is going to read or not. As soon as it sets address, then every slave matches with the address. We'll see this. We don't have time. So steps involved. So it is SDA line become low to all the devices. Then it's going to send the address, and address 0 is going to send the address 0101101 address, and is going to send the readable bit. So slave 1 won't respond, slave 2 also won't respond, but slave 3 matches with the address sent by this master. So suddenly they'll pull the SDA down. Then master will know that okay, particular device is available. Then it's then SDA down. SDA down. This is the acknowledgement bit. Then after that, it is master has to ready to, because master has to ready to reserve send the device, send the message, and as soon as send the message, if master is receiving, it has to pull down the SDA down. If slave is receiving, it has to pull down the message down. Like this, the process is happening. Right. So this is the way the I2 is connected. So within 2 wires, with 3 wires including ground, within 3 wires we can able to connect any number of slaves. So because here we are using addressing to identify the slaves. So it is multiple master, multiple slaves can be achieved. So these advantages only two wires, and suppose the multiple master, multiple slaves, and acknowledgement, no acknowledgement, and hardware is less complicated than UART, a well-known widely used protocol. Slower data disadvantages, slower data transfer than SPI, and the size of data frame is limited to 8 bits, and more complicated hardware than the SPI. So to increase number of GPI pins like in SPI, we can able to use MUX and DMUX. Right. And another is DH211. Maybe I'll share this presentation. You can able to go through this. It is single wire communication, right? Though we are writing DH2, that is a temperature humidity sensor, though we are writing only few lines to get the data, but with single wire, how the communication happens, it is explained very well within a single wire, right? So it is a DHT11, the single wire communication. So only thing is the student who are doing this projects, you know what is done in the back end, what is the communication protocol, how it communicates. Because writing because nowadays we are able to get so many libraries, but we will forget to know what are the things happening behind. Then in the process we can't able to customize any program or hardware to our purpose. So better to know what are the things are running behind for any communication protocol or any device fabrications or packaging extra. Sir, I'm ready to take the question. It's completed.
I request the participants. So if you're having any queries, so you can raise your hand or you can put a question in the chat box.
Okay. Then everybody will have some doubts. What are the things we can able to measure? Let's say we have some. I'll share the screen now. I hope you can able to see the screen now.
Yes, sir.
Yes. So some key site technologies. I'm not marketing any key site product. I have found IoT device battery life optimization. If you are developing any devices, you want to know how much lifetime the battery can withstand, or how many months or how many days. So there are some particular devices are applied in the key site. So what will do your program, because we know that battery is going to power is going to consume in only that during the communication, during the RF communication. But moreover, the RF communication is going to take part in very less number of milliseconds, right? So by using normal multimeter or normal thing, you can't able to do it. So you have to sync, you have to tell that particular devices, I'm going to communicate. Then it will trigger the device to capture all the power data like current voltages, then you capture sample at a very fast rate, and it can able to give the power, so that we can able to optimize the power and what is the power requirement for the particular number of frequent communication, or how we can able to decrease the sampling. All those things can be doing with the device battery life optimization solution given by the Keysight. Otherwise, if we have any multimeter or precision power supply or programmable power supply, all those things can be used in the lab. So how your IoT device is going to behave with, if you have the programmable power supply, you can keep on decrease the voltage, whether the microcontroller is going to reset, and how this radio communication is good. All those things you can able to check. And if you have the precision power supply, or all those things, if you have it, then you can connect the IoT device in precision power supply, keep on continuously monitoring through lab view. Then you can know where the power consumption more during processing uh, or radio communication. Then during the actuation or sensor, you can able to track the power consumption, and accordingly you can able to select the battery. So these we can check it. So do you have any questions?
Participants, if anyone wants to speak with Dr. Sambamurthy sir, please unmute yourself or raise your hand, and we will unmute you. Otherwise, if you don't have a mic, then you may type a question in the chat box. Shekhar garu, ఏమైనా క్వశ్చన్స్ వచ్చాయా చూడండి
సార్.
క్వశ్చన్స్ ఏమైనా ఉన్నాయా చాట్ బాక్స్ లో?
ఏం లేవు సార్.
ఏం లేవా? ఓకే. థ్యాంక్ యూ డాక్టర్ ఈశ్వరమూర్తి గారు. యువర్ క్వశ్చన్ ఈజ్ very good.
Thank you.
We are also learning this battery life and all. It's a very good presentation. I hope all the participants learn the knowledge during this session.
So I request all participants, you can study this book actually. It is because you come to the power. Just a minute, sir. I will share one book name. Enabling the Internet of Things from integrated circuits to integrated system. Right? That is a book. Editor is Massimo Alito. You can go through this book. It contains so many requirements, because everybody should know the practical design. So they have discussed about the power requirements of ADC, DAC, and different architecture. You can able to go through this. I'll share that in the chat box, sir, the title. So thank you, sir.
Thank you, sir. Even though you're quite busy with your academic works and research work, thank you. Rajshekhar garu, please continue.
Yes, sir. So, thank you, Ishumurthy sir, for sharing your valuable knowledge with all of us. Thank you, sir. Thank you so much, sir.
Thank you, sir. Thank you.
Announcement, please.
Sir, participants are asking for book name, sir.
Sir, book name. Yes, sir.
Yes.
I'm pasting that. I'm pasting. I pasted, sir. Enabling the Internet Things. Okay, I'm chatting in the private. Everyone.
Everyone, sir.
Everyone. Okay.
Yes, sir. Enabling the Internet of Things from integrated circuits to integrated systems. Massimo Alito, editor. Yes, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.
A small announcement for the participants. The session, today's session will begin at 2 p.m. Dr. KVSG Murali Krishna Garu, environment professor and civil engineering professor. He delivered a number of talks within the country and outside of the country also. He's very popular. So,
Sir, voice
partic-
really, sir. Voice break అవుతుంది సార్.
okay, participants. Uh, uh, Today at 2 p.m. There will be a session leadership, human values and ethics. The AICTE is now uh, insisting the organizers one session must be uh, in any technical sessions. Along with that, human values and ethics, they're giving highest priority for even for the first BTech students also, even for the faculty also. The ACT is organizing number of programs on human values and ethics. It is a great opportunity for us to listen Dr. KVSG Murali Krishna Garu wonderful speech. I request participants involve actively, okay, that you can enjoy. So, attendance Google form, that is a link form, link will be given at the end of the day session, okay. So, don't miss it. Thank you. Have a lunch break.
Yes, sir. Thank you, sir. So once again, we will meet at 2 o'clock. So for the third session. Thank you, sir.
Thank you.
Shall I close, sir?
Yes, sir. Yes, sir. Please.